Good morning. My name is Yong, and I am a PhD student at Seoul National University. It is a great honor to present at FEST 25 today. In this talk, I will introduce my research, ScaleLFS, a log-structured file system with scalable garbage collection for commodity SSDs. In summary, this work enhances the sustained performance of log-structured file system by parallelizing garbage collection. A log-structured file system, or LFS, is optimized for writes by placing data in an append-only manner. In LFS, new data is written to sequential LBAs, taking advantage of the high performance of sequential writes. When data is overwritten, the previous pages become stale and are marked as invalid. If stale pages accumulate, leading to insufficient free space, LFS reclaims the space through garbage collection or GC. During GC, LFS selects a contiguous range of LBAs as a victim segment and migrates valid pages from the victim segment to free space. However, frequent GC can degrade sustained performance of LFS significantly. Since GC operates in a single thread, it creates a bottleneck. As shown in the figure, application bandwidth drops by up to 68 times after GC is triggered. A straightforward approach to improving sustained performance is to introduce multithreading in GC. However, as shown in the lower right figure, increasing the number of GC threads did not improve performance. This result is due to increased lock contention in the current GC procedure. Therefore, concurrent and scalable techniques for GC are necessary. From our analysis of FTFS, which is a widely used log-structured file system, we identified 4 key obstacles that hinder the scalability of the GC. First, shared resources. The destination segment and page cache for GC are shared among multiple threads, which leads to synchronization overhead. To fix this, we need to dedicate resources to each GC thread. Second, excessive contention in victim selection. The victim selection is exclusively protected, resulting in a scalability bottleneck. If we allow concurrent victim selection, this overhead can be reduced. Third, over-strict metadata synchronization. Segment metadata is protected by a single mutex lock, which forces all threads to wait. Instead, we should enable concurrent segment metadata updates. And finally, coarse-grained data protection. GC threads and IO threads compete for access in file level, creating contention. By switching it to page level, we can reduce contention. To scale out GC, we propose ScaleLFS. It is built on 3 key components: dedicated garbage collector, scalable victim manager, and scalable victim protector. First, dedicated garbage collector or DGC. DGC is a GC thread that has its own dedicated page buffer and destination segment, which reduces resource sharing overhead. Next, scalable victim manager or SVM. SVM enables multiple DGCs to select their victims concurrently using an atomic bitmap. It also allows loose synchronization updates, so multiple threads can update segment metadata at the same time. Finally, Scalable Victim Protector or SVP. It enables page-level garbage collection using a per-file concurrent hash table to reduce contention. Now, let's dive into the details of each component. First, DGC includes a per GC thread data buffer and write stream. A dedicated data buffer helps avoid expensive page cache overhead. As you can see in the figure, when GC starts, DGC selects a victim segment from SVM. Instead of using a globally shared page cache, it loads valid pages directly into its dedicated page buffer. Then, DGC writes the buffered data into its dedicated write stream. At this point, dedicated write stream enables lock-free LBA management in a sequential manner. Next is SVM. SVM introduces concurrent victim selection, or CVS, utilizing two atomic bitmaps, one for dirty segment and the other one for victim segment. Each DGC selects segments with the fewest valid pages as their victims. During the victim selection, the dirty segment bitmap is used to concurrently identify victim candidates, while victim segment bitmap resolves the conflicts from concurrent victim selection. Data rates among DGCs to select same segment as their victims are resolved through atomic test and set bit operation. The DGC that succeeds to set the victim segment bitmap wins. By employing CVS, DGCs can concurrently select victims without encountering lock contention. Another key feature of SVM is loose synchronization updates, or LSU. It allows SVM concurrently update the valid page bitmap, which indicates the pages for GC migration, and the valid page count, which is regarded as the GC cost. We employ an atomic bitmap for VPB and an atomic integer for VPC. However, LSU introduces two side effects: less optimal victim selection, which increases GC cost, and false positive GC rate, which induces unnecessary read I/O. The example of less optimal victim selection is described on the left side of the figure. DGC 0 initially selects segment 1 as its victim due to the lowest VPC. At the same time, optimal victim is changed to segment 0 since other thread has updated VPC. Unfortunately, it can be invisible to DGC 0 since updates to VPC are not tightly synchronized. It induces GC write amplification. However, in our evaluation, the write amplification caused by LSU was negligible. The second side effect, false positive GC rate, is described on the right side of the figure. When the DGC1 reads the first bit in VPB of its victim segment as 1, DGC1 begins GC read for the first page of the victim. However, at the same time, the other thread clears the first bit, indicating that the first page has become stale. DGC1 cannot recognize this update due to LSU. This false positive GC read can induce the data consistency violations. The data from a false positive GC read is stale. Therefore, this stale data should not be serviced to the user to ensure data consistency. To achieve data consistency, we filter out the stale pages by leveraging a node data such as inode or direct node. If the LBA within the node is not same to GC read LBA, ScaleLFS determines the corresponding page as stale one and skip GC writes for it. This procedure are protected by the node level lock, which is already employed in F2FS to protect node data from concurrent updates. Therefore, it does not cause additional lock overhead. The last component is SVP. SVP enables page-level GC by leveraging a per-file concurrent hash table with compare and swap operation. Each thread inserts the file offset of a page before accessing it. When the access finishes, the inserted entry is removed. To prevent reading deallocated memory space, logical deletion is adopted. Logically deleted entry is removed physically by the other thread which firstly discovered it. If a thread finds that same file offset has already been inserted in SVP, the thread waits for its removal. To reduce contention, SVP distributes requests across multiple buckets based on the file offsets. Through SVP, DGC performs GC at the page level, which results in lower contention. We evaluate ScaleLFS on the machine equipped with an Intel Xeon CPU, 160 GB of DRAM, and a Samsung 9A3 SSD. We use 4 KB random writes for micro-benchmarking. Furthermore, we employ file server, bar mail, and OLTP workloads for macro benchmarking. As a real-world application, we evaluate MySQL with YCFS workloads. For comparison, we use FTFS in the Linux kernel and FTFS-L, which operates in pure LFS mode. Additionally, we evaluate MAX as a state-of-the-art scalable LFS and PGC as a parallel GC scheme. ScaleLFS is prototyped on FTFS in LFS mode. In micro-benchmarking, we evaluate our idea with 2 capacity configurations, 30 GB of small partition and the full SSD capacity. The evaluation with the small partition isolates the file system performance by minimizing the impact of SSD level GC. In this configuration, we submit 120 GB of random writes. As shown in the figure on the left, ScaleLFS outperforms other LFSs by up to 7 times in execution time. While other LFSs experience significant bandwidth degradation, ScaleLFS maintains relatively high bandwidth. This result demonstrates that ScaleLFS efficiently scales out GC, ensuring better sustained performance under IO-heavy workloads. Furthermore, to assess how effectively ScaleLFS utilizes the SSD, we measure the write bandwidth submitted to the SSD. As depicted in the figure on the right, ScaleLFS achieves up to 19.6 times higher bandwidth compared to other LFSs. This result reveals that ScaleLFS efficiently utilizes SSD even with the frequent GC. To evaluate on a more practical storage configuration, we also use the full SSD capacity. In this evaluation, we submit 10.3 terabytes of random writes. As shown in the figure, ScaleLFS reduces execution time by 37 minutes compared to FTFS. LFSs operating with pure LFS modes, such as FTFS-L and PGC, exhibit 11 megabytes per second of sustained write bandwidth after both LFS and SSD GC have started. In contrast, ScaleLFS achieves the highest performance without significant performance degradation. This result implies that ScaleLFS is efficient even alongside with SSD GC. For macro benchmarking, we use 3 write-intensive synthetic workloads from FileBench. In this evaluation, ScaleLFS improves throughput by up to 83.1% compared to the other LFSs. The performance improvement is lower than the result in micro-benchmarking due to the less frequent GC caused by loss of file deletions or contention among application threads. To show the performance in a real application, we use MySQL database under YCSB workloads. Initially, 6.5 million records are inserted to fill 70% of total partition capacity. In workload A, which is write-intensive, execution time is reduced by up to 70.4%. In workload B, which is write-intensive, execution time decreases 27.3%. Although write-intensive workloads present a more challenging condition for ScaleLFS, the results demonstrate that it still achieves performance improvement. In this paper, we propose ScaleLFS, LFS designed to accelerate GC through multi-thread friendly optimizations. ScaleLFS leverages multiple GC threads with dedicated strategy and enhances GC concurrency using concurrent data structures and lock-free victim management. Additionally, it introduces a page-level GC procedure to mitigate conflict among threads. Evaluation results demonstrate that ScaleLFS improves performance by up to 7 times compared to existing LFSs. This is the end of my presentation. Thank you for listening.